So now we're going to look at another class of processes that we've mentioned a couple of times called adiabatic processes. Adiabatic processes are processes for which Qn equals 0. In other words, no heat added. Often, these are fast processes. In other words, there just isn't time for heat to flow in and out, or they're well insulated. You can think of them either way, and sometimes it's more appropriate to think of them as one way or versus another. And so I'm just going to write down some equations for this. If we go back to dE internal is equal to dQn minus d work by, right? Then this guy is 0 because the Qn is 0, and so we get CV dt. Remember, because any process, dE internal is CV dt equals, and so the work by, that's that's just minus P dV. That's the work, right? And so we can write this as an equation for dt. We can say dt is equal to minus P dV over the heat capacity at constant volume. And now I'm going to solve for this in a different way. I'm just going to start with the ideal gas law. I'm going to say, look, here's PdV. Here's PV equals nRT, right? And now I'm going to take derivatives on both sides, or more appropriately, I'm going to take differentials. So I'm going to say a d on the left side, which is d on PV, is equal to a differential on the right side, is d on nRT. Right, and you can kind of use the product rule, and this is dP times the volume plus P dV. That's what a d on a multivariable quantity is equal to n and r are constant, so just nr dt, or I can say dt is equal to dP times V plus P dV over nr. And now I have these two things which are equal to each other, right? There's a dt and there's a dt, and so I can say, look, dP times V plus P dV over nr is equal to minus P dV over the heat capacity at constant volume. And now I'm just going to sort of sort this out. I'm going to say dP times V plus P dV is equal to minus nR over CV times P dV. I've got a P dV on both sides, so I'm going to bring this guy over to the other side, and I'm going to say d pressure times volume is equal to plus 1 plus nR over CV times P dV equals 0. So I added this guy over and I factored, if you can follow that in one step kind of thing. And now I'm going to divide through by P, and I'm going to divide through by V. And so this equation is going to become dP over P plus 1 plus nR over CV dV over V equals 0. Right, if I divide both terms by P, this P goes away and I get a dP over P. And then if I divide both terms by V, this V goes away and I get a dV over V. And so everything looks the same except I have a dP over P and a dV over V. And I'm going to come back up here to the top. I'm just going to simplify this a little bit, right? And so if you look at 1 plus nR over CV, that's equal to CV plus nR over CV, which is equal to CP over CV. we call this thing gamma. And so this is the same as that, is the same as that, is the same as that. And so what I get is dP over P is, plus gamma dV over V is equal to 0. For adiabatic processes, we're trying to come up with a sort of a non-differential relationship, and so I can actually just integrate both of these, right? And when I do that, I get log of P plus gamma log of V is equal to some constant. Right? You can just call this, right? These are indefinite integrals, so you can just add a constant onto each of those integrals and then just add them together, call them a constant and move to the other side and call them a different constant, right? And so this is log of P plus log of V to the gamma is equal to a constant. And then I can take the product of that, so log of P times V to the gamma, I'm just doing log stuff now here, is equal to a constant, right? This is because A log B is equal to log of B to the A, right? That's one of those log identities. And this one is log A plus log B is equal to log of AB. And so now I have this. Well, I can raise both sides to the e, or e to the both sides, right? And this gives me PV to the gamma is equal to e to the constant, which is just a constant. And so this says for adiabatic processes, PV to the gamma is a constant where gamma is equal to Cp over Cv. And we can evaluate this thing, you know, for a diatomic, for a monatomic, this is equal to 5/2 nR over 3/2 nR, which is just 5/3. And so this is for a monatomic. For a diatomic, gamma is 7/5. By the same argument, it's 7/2 nR over 5/2 nR, and you get 7/5. So this is like 1.67, this is like 1.4, and so on. I think for polyatomic it ends up being 1.33 or something like that. And so what this is saying is that PV to the gamma is a constant for an adiabatic process. And so let me just draw a picture here and say, look, suppose we had some process here, right? And it was adiabatic. And so I went from this position 1 to this position 2. Then if this is an adiabatic process, P1 V1 to the gamma is equal to P2 V2 to the gamma. Anywhere along this curve, in fact, if I evaluate PV to the gamma, it doesn't change. And so this is a tool for evaluating quantities at both ends. So if I know the pressure and volume here, and I want to know what the volume is at this new pressure, if it's an adiabatic process, I can use this equation to determine that volume. So for adiabatic processes, we said PV to the gamma is a constant. Again, gamma is the ratio of the heat capacity at constant pressure to the heat capacity at constant volume, right? And so I can use the ideal gas law to get slightly different versions of this. For example, I can say V is equal to nRT over P, And then I can substitute it, so I can say P times nRT over P to the gamma is a constant. And this becomes P times nR to the gamma, T to the gamma. I could have had nRT all to the gamma, but I wanted to separate these out over P to the gamma is a constant. But these guys are a constant because this number never changes. It's the number of moles of ideal gas I have, and R is a constant. So I can just cancel that out and change that to constant. Prime still just a constant. And this becomes P to the 1 minus gamma, T to the gamma is a constant. Again, a different constant, but a constant. And so if I evaluate this quantity at 2 points that are on an adiabatic curve, they have to come out the same all the time. Similarly, and I'll let you do this on your own, you can show that T V to the gamma minus 1 is also a constant. And so, here's an equation, here's an equation, here's an equation. They're all different ways of using the ideal gas law and the adiabatic equation to write the adiabatic equation in terms of pressure and volume, or in terms of pressure and temperature, or in terms of volume and temperature. So here's an example. It says an ideal diatomic gas at 80 Kelvin is slowly compressed adiabatically to 1/3 its original volume. What's its final temperature? And so here they're talking about temperature and volume in an adiabatic process. And so I'm going to grab my adiabatic equation for that, which is T V to the gamma minus 1 equals a constant. Right? And so I have T1 is 80 Kelvin, and V1 is whatever it is. And then T2 is question mark, and V2 is V1 over 3, right? I also know that gamma, which is CP over CV, is 7 halves NR over 5 halves NR, because it's a diatomic, which is just 7/5 or 1.4. And so now I can say, look, T1 V1 to the gamma minus 1 is equal to T2 V2 to the gamma minus 1. What I want is T2, and so I have T1, so I'm going to solve for T2, and I'm going to get T2 is equal to T1 V1 to the gamma minus 1 over V2 to the gamma minus 1. And so this is equal to just T1 times V1 over V2 to the gamma minus 1. T2 is equal to T1 times, and so we know what these are. This is V1, and this is V1 over 3. That's its final volume to the gamma minus 1. Well, V1 over 3, this just becomes T1 times 3 to the gamma minus 1. Well, gamma is 7/5, and so gamma minus 1 is 2/5, or 0.4, right? And so this is 80 Kelvin times 3 to the 0.4. I get 124 Kelvin. So I've compressed it, I've done work on it, I've heated it up a little bit, I've raised its temperature, but I haven't allowed heat to flow in or out. Right? I've raised its temperature by doing work on it, not by allowing heat to flow.